Good afternoon, dear abstract algebra students. So today we shall formally start discussing the lesson 1 in the learning packet that I have provided you last week. So for this lesson, the intended learning outcomes would be for you to be able to perform specified binary operations on a particular set and verify whether or not a given operation qualifies as a binary operation on a given set. So in your first activity, in that learning packet, you were asked to perform the operation define asterisk on the set of integers as a operation b is equal to the sum of a and b divided by the difference a minus b. Okay, as an illustration, we have here 2 operation 4. By definition, will just be the sum 2 plus 4, then divided by the difference 2 minus 4. So you have 2 plus 4 is 6, then this is 2 minus 4 is negative 2, then divide 6 by negative 2, so the answer would be negative 3. Okay, let us now try to answer this activity. So here in number 1, you have 6 operation 4. So we write 6 operation 4. So by definition, that should be equal to the sum of 6 and 4 divided by the difference 6 minus 4. So this would be equal to 10, that is 6 plus 4, then divided by 6 minus 4 is 2, so the answer is 5. Okay, so we need to determine the result whether it is an integer or not. So the result is an integer, so the answer is 5, which is an integer for number 1. Number 2, we have we have 5 operation 2. So 5 operation 2 will be equal to 5 plus 2 divided by, let me erase this first. Divided by the difference 5 minus 2. So we should have 7 divided by 7 divided by 5 minus 2 is 3. Okay, so the answer would be 7/3, 7/3. So that would be 2 and 1/3. The result is not an integer since 7 is not divisible by 3. Then in number 3, you have there 4 operation 4. So 4 operation 4. By definition of the operation, we have 4 plus 4 divided by divided by 4 minus 4. So, we would have 8 divided by 0. But we know that division is not defined when the divisor is 0. So, the answer would be not, excuse me. So, the answer is not even a real number. Hence, it is not an integer. So, the answer does not exist and it is not a real number. Okay, I hope you got that. We would check. Okay, notice that the answer key is given here in the last part of the learning packet. So the answers are 7. Number 1, 5, which is an integer. Then number 2, you have 7 over 3, which is, rather, in number 1, 5, which is an integer. In number 2, you have 7 over 3, which is not an integer. Then number 3, you have 8 over 0, an indeterminate or undefined. Okay? In the next part of the learning packet, you were asked to read pages 8 to 11, and then 1 to 8, and 11 to 18, and 20 to 25. We have already discussed what are written in pages 1 to 8. And 11 to 18 actually is just a review of advanced algebra. Okay, so the algebra of matrices, algebra of complex numbers, then the Euler's formula, the application of trigonometry in complex numbers, and so on. So you'll just have to review all of those, recall your discussion in advanced algebra. But you can still ask me through our group chat. For now, we shall just focus on what is required to finish this learning packet. Okay? So, first, let us refer to the definition of binary operation in our textbook. Okay, let us move to our textbook here. So, a binary operation asterisk is defined, or on a set S, is a function mapping the cross product of S to itself into S. Okay, so to denote that, if you recall, last time when we have discussed functions, so here it is said that the operation asterisk pairs or maps the cross product S cross S into S itself. Recall that the cross product S cross S will be composed of ordered pairs of elements in S. So for example, A and B and A, B and C, say let us take S to be the set containing A, B, and C. So the elements of S cross S would be AA, AB, AC, BA, BB, BC, and CA, CB, and CC. So those would be the ordered pairs, elements of the cross product of S to itself. Now take note that each, since asterisk is a function, each of those ordered pairs will be paired with a unique element which is also in S. Let us take, for instance, it so happened that AB the ordered pair AB is paired with, let's say, C, and then Let's take another example. Say the ordered pair BB is paired with, let's say, A. Okay? So, the notation for binary operation would be this one, A operation B. Meaning, this correspondence, so we see here that asterisk of AB is C. Meaning, in the conventional notation, since AB is being paired with C, so in the conventional notation, we can just say A operation B is C. Okay? Also, we see that BB is being paired with A. That would mean that B operation B is equal to A. Okay? Based on this example. Now, every familiar binary operation actually are the four fundamental operations. Let us apply the concept on, let's say, addition. Addition actually is a binary operation. Addition is a binary operation pairing the cross product of real numbers to itself, so that would be R squared, to itself, a set of real numbers. And take note that in addition, the ordered pair, let's say 2, 3, is being paired with 5. Diba? Why? Because 2 plus 3 or 2 added with 3 is just 5. That is why in our conventional notation, we write 2 plus 3 equals 5. Okay, so that is what we meant by binary operation. Take note, binary operation is a function. When we say function, there should be an image for each element of the domain. Meaning, each ordered pair should be associated or paired with a unique element in the codomain. There should always be an answer, and that answer should be in the set in the codomain. So that is why we say that a binary operation should always be well defined. There should always be an answer, and that answer should be in the set. That is why such concept is highlighted in our learning packet. If we would try to read that here, we should keep in mind that for an operation to be classified as a binary operation, it should satisfy two conditions. First, there should always be exactly one answer or one result. That is, the operation must be well defined. And second, such result should also be an element of the set where it was defined. We call that property closure with respect to the operation. Okay? Both conditions must be satisfied before we can say that the operation is a binary operation in the given set. Okay? So, we would also have to consider what set is the operation being defined. So, let us proceed to activity 2. In our activity 2, we are to verify whether or not the given operation is a binary operation in the given set. If not, we have to state the condition which was not satisfied for it not to be a binary operation. Okay. In number 1, we define the operation asterisk on the set of real numbers R, wherein A operation B is the product of the sum a plus b and difference a minus b. Okay? Now, actually the answer are detailedly discussed in detail in the next page. Okay, so we let two elements x, y, b in R, and then since addition is closed in the set of real numbers, that is, if we add two real numbers, the answer is also a real number. So it should follow that x plus y and x minus y are both real numbers. Okay? Why? Because x minus y is defined as x plus negative of y. Diba? So that is still addition of real numbers, because if y is a real number, then it's negative. Negative y is also a real number. And then since the operation multiplication is closed in R, the product therefore of the sum x plus y and the difference x minus y should also be a real number. Meaning, the product or the result when we operate x by y is also a real number. Therefore, the first operation is a binary operation. Okay. Let's try number 2. Number 2, the operation is defined as follows. Asterisk on the set of rational numbers where A operation B is AB, the product AB plus 1. So here we have the solution. Excuse me. Number 2, the set of rational numbers in operation B. Now that is activity 3, I'm sorry. Activity 2 is the operation asterisk on the set of integers. The set of integers where A operation B is A to the B. Okay, the set of integers wherein A operation B is A to the B. Okay, narong ko ganin nagbasa. That was activity 3. Okay. So we say that the operation is not a binary operation. Why? We show a counter example wherein one of the properties is not satisfied. So we have here, we take, let's say for example, 2 and negative 1. Both 2 and negative 1 are in Z because both are integers. But note that if we apply the operation, 2 operation negative 1 will be 2 to the negative 1. In other words, that will just be the inverse or the reciprocal of 2, which is 1/2. But we know that 1/2 is not an element of Z, that is not an integer. Therefore, even if there is a result of 2 operation negative 1, there is a result 1/2, but 1/2 is not in the set where the operation was defined, meaning the operation is not closed, or that is Z is not closed over the operation asterisk. Thus we say that the operation asterisk is not a binary operation on Z. Okay? Number 3. Let's go back to our page. Number 3. Okay, number 3, activity 2. Asterisk on the set of positive integers Z plus where A operation B is the minimum between A and B, meaning whichever is small between A and B, that would be the answer of A operation B. So we say that if we let X and Y be positive integers, so by definition, X operation Y would be the minimum between X and Y. Meaning, the answer would be x if x is less than or equal to y. Okay, since the smaller one would be the answer. Or, it would be y, meaning there are two possibilities. If x is less than or equal to y, the answer would be x. But if x is greater than or equal to y, the answer for a operation, x operation y would be y. Either way, the answer for x operation y would always be a positive integer because both x and y are positive integers. Therefore, the operation asterisk is a binary operation on z. Okay, so that is for activity number 2. Let us go back to our book and have additional knowledge and understanding about binary operations. Okay, so as mentioned earlier, the usual addition is a binary operation on the set of real numbers. Also, the usual multiplication is also a binary operation in the set of real numbers. Okay? And it could be proven that addition and multiplication are both binary operations on the following sets: complex numbers, integers, positive, real numbers, positive integers. Okay. However, one of the 4 fundamental operations can be proven not to be a binary operation in the set of positive integers. So, take for example, subtraction. Subtraction in the set of positive integers. Recall that although 5 and 3 are both in z+, but if you apply subtraction there, the answer would be -2, which is not anymore an element of z+. Meaning, subtraction is not a binary operation in z+. Okay? Let us now talk about induced operation. Induced operation uses the concept of subsets. Okay, so there are now two sets under consideration. We have here definition 2.4. Let asterisk be a binary operation on S. So given that it's already given that the operation is a binary operation on S, and let H be a subset of S. The subset H is closed under the operation asterisk if for all elements A, B in H, we also have the result A operation B in H. Okay, so the subset would be closed under the operation if the result of every ordered pair in H would still be in H. Okay, if this so happen, then the operation is what we call an induced operation. Formally, we say that the binary operation on H given by restricting asterisk to H is the induced operation of asterisk on H. Okay? Therefore, common sense would tell us not all binary operations on a set would still be a binary operation in all of its subsets. Just take, for example, this one. We know that subtraction is a binary operation in Z. Why? Because if we subtract two integers, the result would be still an integer. So, subtraction, again, is a binary operation in Z, set of integers. But operation subtraction is not a binary operation in Z plus, even if Z plus is a subset of Z. Diba? Z plus is a subset of Z, but the operation subtraction is not closed in Z plus. Therefore, the subtraction is not an induced operation from Z to Z plus. Okay, so as an example here, our usual addition on the set R is or does not induce a binary operation on the set of non-zero real numbers, even if non-zero real numbers is just a subset of R. Why? Because take for example 2 and negative 2, which are both elements of R asterisk, or both are non-zero. But if you would add a 2, the result would be 0, which is not an element of R asterisk, meaning R asterisk is not closed under the usual addition. Okay, another example. Let addition and multiplication be the usual binary operations of addition and multiplication on the set Z. Okay, integers. Let H be the set of the form n squared, wherein n is a positive integer, meaning H would contain all perfect squares of positive integers. We are to determine whether or not H is closed under addition, then next under multiplication. So we need to observe that 1 squared, which is 1, and 2 squared, which is 4, are both in H, but the sum 1 plus 4 is 5. But we cannot find an integer so that the square is 5, meaning 5 is not a perfect square. 5 therefore is not in H. Therefore, H is not closed under addition. So that means to say that addition is not an induced operation from Z to H. For the second operation, we now take arbitrary elements of H. Arbitrary meaning we take symbols to represent any element of the set H. So let's take R and S to be elements of H, but if we are to mean that R and S are both in H, meaning there should be positive integers M and N, so that R is the square of N and S is the square of M, meaning both R and S are perfect squares, and there are integers N and M for which the squares are R and S respectively. Now, if we are to multiply R and S, therefore, by substitution, it will become N squared times M squared. But by law of exponents, this can be written as the square of the product N times M, meaning R times S would be a perfect square because there is an integer N times M whose square is the product R times S, which means to say that R times S is still an element of H. That would mean that multiplication is an induced operation from Z to H because H is closed under multiplication. Okay? Also, if we would go back to our advanced algebra, it could be proven that addition, subtraction, multiplication, and composition of functions are all binary operations in the set of real valued functions. Why? Because the sum of function is still a function. The difference of two functions is still a function. The product of two functions would still be a function. The composition of two functions would again be a function. Okay. Let us now take examples wherein the operation are not quite familiar, meaning not one of the four fundamental operations. For example, those which we took up in activity 2. Okay? So here we have example 2.9, defined on the set of positive integers. We have here asterisk prime by a asterisk prime b, or a operation b is a. So by this rule, it would mean to say that what is mentioned first would always be the answer. So we say 2 operation 3 is 2. 25 operation 10 is 25. 5 operation 5 is 5. So this would follow that the answer would always be an element of the given set, because in the first place, the first element mentioned is an element of the given set. So this operation is a binary operation. In the next example, we have again an operation on z plus, or positive integers, give us symbolized by asterisk double prime, defined by a operation b is a operation b, or a asterisk b plus 2, where asterisk is defined in example 2.8. Going back to example 2.8, it is asterisk means the minimum of the two. Okay, the minimum of the two. So for example, in this example, we have 2 operation, or 4 asterisk double prime 7 would be 6. Why? Because, let's solve it here. 4 asterisk double prime 7 would be, by definition, it is a asterisk b plus 2. So this would be 4 asterisk 7 plus 2. But this asterisk is taken as the operation in example 2.8. So if we would go back to example 2.8, asterisk equals the smaller of a and b, so the minimum between the two numbers. So for 4 asterisk 7, the minimum is 4, so the answer is 4 plus 2, so the answer will be 6. Okay, so that is why we have here 4 asterisk double prime 7 is 6. Okay, you can just verify the other 2 examples. Okay, next we have the properties of binary operations. First property is the commutativity. A binary operation asterisk on a set S is said to be commutative if and only if A operation B is the same as B operation A for all elements A and B of S. Meaning, no matter how we rearrange the order of the terms being operated, the result will be the same. In other words, if we write that if we write that using the ordered pair notation. So it should be that what is being paired with AB, okay, the image of AB should be the same as the image of the ordered pair BA. Meaning if AB is being paired with C through the operation, it should also be the case that the element paired with BA is also C. Meaning A operation B is C, should be that B operation A should also be C. Take note that this should be true for any element of the cross product S cross S. Next, we have associativity. The binary operation on a set S is said to be associative if the product A operation B operated to C would be the same as A operated to the product of B and C for all elements A, B, and C of S. Meaning no matter how we regroup the terms being operated, the result will be the same. Okay? It's different from commutativity because in commutativity the orders were changed. Here only the grouping. Okay? Let's try to apply the concept of associativity in one of our examples. Let us go back to our learning packet. Okay, activity 3. In activity 3, we need to determine whether the binary operation defined is commutative and whether it is associative. In the first number, in number 1, activity 3, the operation is the usual subtraction defined on Z, set of integers. So here is the solution. Here we have a counterexample because it is clear that subtraction is not associative. Diba? If we take the elements 1, 2, and 3 of the set of integers, note that 1 operation 2 will be 1 minus 2 or negative 1, whereas 2 then 2 operation 1 is 2 minus 1 or 1. So 1 operation 2 is not the same as 2 operation 1, meaning the operation asterisk is not commutative. Okay? So daily commutative. At the same time, if we have the expression 1 operation the quantity 2 operation 3, by definition 2 operation 3 is 2 minus 3, which would give negative 1. So this will become 1 operation negative 1, which is equal to 1 minus negative 1 by how we define the operation asterisk. But negative of negative 1 is 1. So this will become 1 plus 1 or 2. While if we rearrange, we change the grouping and consider the first two terms first, operating the first two terms first, we would have the quantity 1 minus 2 operation 3, which is by definition 1 minus 2 operation 3, that would be negative 1 operation 3 or negative 1 minus 3 or negative 4, meaning the two operations do not give the same answer if we change the grouping. That is 1 operation the quantity 2 operation 3 is not equal to the quantity 1 operation 2 operated to 3, meaning the operation is not associative. Next, in number 2 of the same activity, we have the operation on the set of rational numbers Q, where A operation B is defined to be A times B plus 1. Okay. So here, we have A operation B as defined is A B plus 1. But then we know that multiplication is commutative in Q. So AB can be written as BA. So it will be equal to BA plus 1. So just copy plus 1. But BA plus 1, by definition of asterisk, will just be B operation A. Meaning, A operation B is equal to B operation A. Hence, we say that the operation asterisk is commutative. But, we suspect that it is not associative. If so, we would show a counter example. So, we take the elements 1, 2, and 3 of the set of rational numbers. Note that if we would first consider operation 3, this will be 2 times 3 plus 1. So, we have 1 operation quantity 2 operation 3 will be 1 operation the quantity 2 times 3 plus 1. So that would be in short 1 operation 7. But 1 operation 7 by definition of asterisk is 1 times 7 plus 1. So it will be 8. While if we consider the first two, operate the first two elements first, that is the quantity 1 plus 2, before we operate it to 3, so we would have the quantity 1 times 2 plus 1, operation 3, but 1 times 2 plus 1 is 3, so it will be 1 operation 3, which is equal to 3 times 3 plus 1, which is equal to 10. Take note that they do not yield the same answers. So that is 1 operation, the quantity 2 operation 3 is not equal to the quantity 1 operation 2 operation 3, meaning the operation is not associative. Okay? Next, in number 3, we have the operation asterisk, again defined on the set of rational numbers Q, where A operation B is AB over 2, the product of A times B divided by 2. So, note that A operation B, by definition of asterisk in number 3, is AB over 2. But again, AB is the same as BA. So, copy over 2. So, it will be BA over 2, which again by definition of asterisk is B operation A. So it is always the case that A operation B is equal to B operation A. So we say that the operation asterisk defined in number 3 is commutative. But again, we suspect that it is not associative. So we see here, if we take the elements 1, 3, and 5, so note that 1 operation the quantity 3 operation 5 will be 1 operation 3 times 5 over 2, which is equal to 1 operation 15 over 2, which is by definition of asterisk in number 3, that will be the product 1 times 15 over 2, or simply 15 over 2. While the quantity 1 operation 3 operation 5 will be 1 times 3 over 2 operation 5, which is equal to 3 over 2 operation 5, or 3 halves times 5 over 2, which is equal to 15 halves over 2, or 15 over 4. Hence, we see that 1 operation the quantity 2 operation 3 is not equal to the quantity 1 operation 2 operation 3. Hence, the operation defined in number 3 is also not associative. Okay, so that is all of our uh, learning packet. Let us just finish reading the pages, the assigned pages in our book. Here we have the proof that composition of functions is associative. Okay. Recall that when we say composition of functions, we define, let's say, f circle f circle g of x is defined as f of g of x. Okay, so we have here the proof. If we have f circle quantity g circle h of x, so consider this as just one function. So this would be f of this function of x. So this f of g circle h of x. But then g circle h of x will be g of h of x. So we'll have f of g of h of x. But if we would have it the other way around, if we consider f and g first, composition of f and g, so we have f circle g quantity circle h of x would be, this would be the first function, f circle g of the second function h of x. So this would be the element in the domain this time, and the function is f circle g. So we'll have f of g of this one. So that is why we have f of g of h of x, which is the same as this if we compare the two, meaning they have the same result. So the composition of functions is indeed associative. Now we have here operation tables. Okay, just like what we have in our elementary days, we try to consider elements 1 to 10, then memorize the product. So that's the multiplication table of numbers 1 to 10. Here we have operation tables of elements a, b, and c. So if we take elements a, b, and c and consider this table showing us the results, so here it means that a operation a is b, a operation b is c, and a operation c is b. B operation a is a, b operation b is c, b operation c is b, and so on. Okay, so we see that a operation b is c, but b operation a is a, meaning they are not the same. Hence, the operation defined in this table is not commutative. Okay? Why? We can easily see that a binary operation defined by a table is commutative if and only if the entries in the table are symmetric, or that would be mere reflection, with respect to the diagonal that starts at the upper left corner of the table and terminates in the lower right corner. That means this line here. Okay, so the other entries should be symmetric with respect to this line or to this diagonal. Meaning, if B operation A is D, it should be that A operation B is D, so D should be the element here. So the element here should be D. Also, if C operation A is A, it should be that A operation C should also be A. And then B operation A is A, so A operation B should also be A. Okay, so if we continue in that manner, we would have to obtain this one, this table. Okay, so that would be commutative operations in tables. Now, if we would try to check associativity in the operation of tables, the task would be quite tedious because we would have to consider all possible triples of the elements in the table. Okay, so there would be no other way of checking whether or not the operation defined in the table is associative, but only to check all possible triples and verify whether the answers would always be the same. If one triple would not give the same answer, if we regroup, then the whole operation defined in the table is not associative. Okay. Let us now move on to a very important binary operation. Let Z sub n denote the set containing the integers from 0 is 2. This is 2. Zero up to n minus 1. Okay, so this is just a finite set. And note that these elements here, 0, 1, 2, up to n minus 1, would be the possible remainders if we divide a number by n. Okay? We can then define an operation plus sub n. We call it addition modulo n. Addition modulo n. Okay? We can define that as let's say A plus sub n of plus B as equal to R, wherein R will be an element of Z sub n, wherein R is the remainder when A plus B is divided by n. That is, we can find quotient and the remainder, meaning we can express A plus B as the product of an integer q and n plus the remainder r, wherein r is not negative, so it should be greater than or equal to 0, but less than the divisor n, meaning r would be one of these elements here. 1, 2, up to n minus 1. So, sa particular example, let's say z sub, let's say 5, z sub 5 by definition of z sub n would be 0 to 4. 0, 1, 2, 3, 4. Which are the possible remainders when we divide a number by 5? Isn't it? So by this definition, addition modulo, we call this addition modulo n. So we have addition modulo 5. If we have to add, let's say, 2 plus 3 modulo 5, in ordinary addition, the answer should have been 5. But 5 divided by 5 is 1, remainder 0. Meaning, 2 plus 3 modulo 5 is 0. Okay? We call this modular addition. Okay? We now consider a modulo or a divisor. And then the answers, the possible answers would be the remainder when you divide the ordinary answer by the modulo. So, for example, here, if we have 4 plus 3 modulo 5 would be, ordinarily 4 plus 3 is 7. But if you divide 7 by 5, the quotient would be 1, and the remainder is 2. So, 4 plus 3 modulo 5 is 2. Okay? Or for example, here we have let's say 4 plus 1 modulo 5 is 0. So in other words, if we have let's say 7 plus 6 modulo 8, this would be equal to equal to 5. Why? Because 7 plus 6 is ordinarily 13, but if you divide 13 by 8, the quotient is 1 with a remainder of 5. So that is why we have 7 plus 6 is equal to 5 in modulo 8. Okay? Similarly, we can also define similar operations as the 4 fundamental operations modulo n. We can also define in the same manner subtraction modulo n, multiplication modulo n, and so on. So for example, if we have 3 times 4 modulo 5 is 2. Why? Because 3 times 4 in ordinary multiplication is 12. If you divide 12 by 5, the quotient is 2, remainder 2. So, the remainder is always the answer. So, that is why 3 times 4 modulo 5 is 2. Or another example, 4 times, let's say 7 modulo 9 will be 4 times 7 is 28. But in modulo 9, that 28 will just become 1 because the remainder would be 1. Okay? Or in subtraction, suppose we have 5 minus 6 modulo 3. That will be equal to 2. Why? Okay. take note that the modulo this time is 3. In ordinary division, subtraction, 5 minus 6 is negative 1. Negative 1. I'm sorry. But, if we divide negative 1 by 2, so that the remainder is not negative, this should be the modulo here is 3. Sorry. If we divide negative 1 by 3, so that the remainder is not negative, so you have here express negative 1 as 3 times something plus a non-negative integer. So this should be negative 1 plus 2. Isn't it? Why? Because negative 3, that is 3 times negative 1 plus 2 is negative 1. Otherwise, you would not have a positive remainder here. That is why negative 1 will be equal to positive 2 in modulo 3. Okay? You got that? Let's take another example. So suppose we have 7 minus 9 in modulo 10 would be 8. Why? Because supposedly the difference is negative 2, but if you divide that by 10, so that the remainder is not negative, your quotient should be negative 1 plus 2, so that you plus 8. Plus 8. So that negative 10, because negative 10 plus 8 is negative 2. So the remainder is 8. Therefore, 7 minus 9 in modulo 10 is 8. Okay? The same concept can be applied also in division. So, but the process is quite different. So, for example, if you are to divide 6 by, let's say, 4, divide that in modulo 5. So, let this be symbolized by x. If 6 divided by 4 is x, that means 4 times x should be 6. Meaning, what do we multiply to 4 so that the remainder, when we divide it by 5, is 6. But then 6 can be expressed only as 1 in modulo 5. Okay, take note that we are in modulo 5. So we are looking for x, so that 4 times x equals 1 in modulo 5. But, meaning 1 should be a multiple or a number same as 1 in modulo 5 should be a multiple of 4. But then 1 note that 1 in modulo 5 is congruent to 6 or equal to 6 in modulo 5. It is also equal to 11 in modulo 5. It is also equal to 16 modulo 5. Isn't it? And 16 is now a multiple of 4. So, we say that 4 times 4 is now equal to 1 in modulo 5. Modulo 5. Meaning, 6, which is the same as 1, divided by, let's make this bigger, divided by 4 in modulo 5 is equal to 4. Okay? See that? Again, how 6 divided by 4 in modulo 5 is the same as 1 divided by 4 modulo 5. Why? Because 6 is the same as 1 in modulo 5, since if we divide 6 by 5, the remainder is 1. Okay, take another example. Let's have another example for division, modular division. Say, for example, 2 divided by 3 in modulo 7. Suppose this is x. That would mean 3x. 3x should be equal to 2 in modulo 7, which means we have to find the number multiplied to 3 so that the remainder is 2 when you divide it by 7. But then 2 is the same as 9 in modulo 7. Modulo 7. So, 9 is already a multiple of 3. 9 is just 3 times 3. So, we have 3 times 3, therefore, is equal to 2 in modulo 7. 7. Oops, sorry. Hence, 2 divided by 3 in modulo 7 is equal to 3. Why? Because 3 times 3 is equal to 2 in modulo 7. Okay, so that would be all for our first topic. You may now start answering the learning task in our learning packet. So again, you can just write your answers on clean sheets of paper, take a clear picture, and then send it to me through a personal message. Okay, but you would have to also write your name, the name of the subject, then the title of the activity. That is learning task number 1 for binary operation. Okay, so that would be all. You may want to subscribe and hit the notification button so that you would be notified whenever I upload new videos for abstract algebra. Okay, good day and goodbye.